In this video, we're going to look at solving problems to do with circular motion. It would be helpful if you've already learnt about uniform circular motion and centripetal acceleration before commencing with this video. There are three different types of circular motion problems that can come up in exams. The first one is the most straightforward, which is horizontal circles. It gets slightly more complicated when you move on to vertical circles, and then finally the most challenging is circular motion on a banked track involving banked problems. So the first type of question we're going to look at is horizontal circular motion problems. With horizontal circular motion problems, all you need to remember is that you need to calculate the force, which you can find using F equals ma towards the centre of the circle. In more complicated questions, it could be that force is generated by the gravitational force, for example, in which case you need to use a gravitational force equation to work out the force, and then from there you could be expected to calculate the velocity that the particle will be moving using F equals mv squared over r. We're now going to move on to the next slide and have a go at answering some questions. So we have two questions on here. I'm just going to give you a few pointers to help you with solving this one. The first of all says calculate the centripetal tension force in a string used to whirl a mass of 200 grams around a horizontal circle of radius 70 centimetres at 4 meters per second. So here you just need to make sure everything's in the right units, and then you're going to use a centripetal force equation that is F equals mv squared over r. That force is equal to your tension. In question 2, it says calculate the maximum speed that a car of mass 800 kilograms can go around a curve of radius 40 meters if the maximum frictional force available is 8 kilonewtons. So the first thing to do is make sure everything's in the correct units again, and then you can use F equals mv squared over r, where your radius obviously is your radius, your mass is your mass, but this time the maximal frictional force will be equal to the centripetal force acting on your vehicle, and that will give you the maximum speed that a car could safely travel around that circle. If you pause the video now and try and complete those two questions, we'll look at the answers on the next slide. So here is question 1. What we should have done here is you should have used the F equals mv squared over r, acting towards the centre of the circle, use that equation there, and then you're going to have to convert your 200 grams into 0.2 kilograms, you can convert your 70 centimetres into 0.7 metres, and then you're going to do mv squared over r to get tension of 4.6 newtons. In question 2, it said calculate the maximum speed that a car of mass 800 kilograms can go around a curve of radius 40 meters if the maximum frictional force available is 8 kilonewtons. So the car will skid if the centripetal force required is greater than 8 kilonewtons. So we're going to use our 8 kilonewtons this time as our force. Remember that's 8,000 newtons. That's the only unit conversion we need for this question. And then what we're going to do is we're going to put that into the equation. So we get F equals mv squared over r. Rearrange to find v squared is f times r over m, and then we find that v squared is equal to 400, and square rooting that gives us 20 meters per second. So with vertical circular motion questions, it becomes slightly more complicated. Here you're still going to use F equals ma towards the centre of the circle, but here the reason it's more complicated is that F is the resultant force acting towards the centre of the circle. This is always the case, even with the circular motion in a horizontal circle. It's just unusual if you're using a horizontal circle for there to be extra forces acting. The only time that could be is if there was a frictional force on a car, for example. In this case, when you've got a vertical circle, you're going to also have to consider the object's weight as well as the tension in the string, which makes it slightly more complicated. So looking at the example we've got here, you can see at the top, the resultant force is going to be weight plus the tension, whereas looking at the bottom, the resultant force is going to equal the tension minus the weight. So now going to have a look at another question where we're using our information that we had from the previous slide. It says a mass of 300 grams is whirled around a vertical circle using a piece of string of a length 20 centimetres at 3 revolutions per second. It wants you to calculate the tension in the string at positions A at the top, B the bottom, and C the string when the string is horizontal. It also gives you information about the angular speed in this question. So the key thing remember that you want to do this time is remember at A, the resultant force is going to equal your weight plus your tension in the string. At B, the resultant force is going to equal tension minus the weight. And at C, the resultant force is just going to equal the tension. So hopefully you can use that information in the question now to answers part A, B and C. I would suggest you pause the video Once you've got an answer to each one, listen to the video again to see if you've got the correct answers to those problems. So set in part A, at the top, both the weight of the mass and the tension of the string are pulling the mass towards the centre of the circle. So our resultant force is mg plus your tension. So our resultant force, remember, is F equals mv squared over r, or F equals mr omega squared, which is the centripetal force. That equals mg plus t. So rearranging that, our tension at the top is going to equal our centripetal force minus our weight. And working that through, you find that tension at A is 18.4 newtons. At point B, the weight is now acting away from the centre of the circle, so therefore your resultant force, or the centripetal force, is going to equal the tension minus your weight. So rearranging that to find what tension is, where you're going to have to add your centripetal force to the weight of the material, as shown in this line here. And if you add those things together and calculate them, you find that at the bottom of the string, the tension is 24.3 newtons. In part C, for the horizontal piece of string, the weight is acting perpendicular to the direction of the centre of the circle, so therefore has no effect on the centripetal force. So what you want to do now is just say that the centripetal force is just going to equal your tension. So your tension in the rope is equal to mr omega squared. So tension at C is just 21.3 newtons. We're going to look at a slightly more challenging question here, question 4. So he wants you to calculate the maximum speed that Pat could drive over the bridge for Jess to stay in contact with the van's roof. So I don't know if there's any Postman Pat fans out there, but imagine Postman Pat driving along, he's forgot to put Jess in the van, Jess is sat on the roof, and as he comes flying over the bridge, what's the maximum speed that would allow Pat to drive over the bridge and keep Jess in contact with the van's roof? I'm going to assume that Jess is a distance of 8 metres from the centre of curvature. Now, in order to be able to answer this question, the thing that you're going to need to think about, and I'd like you to think about this now, is what are the conditions needed for Jess to remain in contact with the van's roof. So I'd like you to pause the video and just have a think about what conditions will be needed for Jess to remain in contact with the van's roof. Okay, so hopefully you've paused the video and had a thought. I'm going to give you the answer to that question now because it'll help you move on with how to go about tackling the question. So Jess will remain in contact with the van's roof as long as the reaction force, is greater than 0. So if the reaction force between Jess and the van is greater than 0, Jess will remain in contact with the van's roof. Now, based on previous questions that we've looked at, we need to consider the other force that are acting on Jess at the moment in time, which is the weight, mg, and also the centripetal force. Okay, and there's also the reaction force between Jess and the van's roof. So as long as the reaction force is 0 or higher, Jess should remain in contact with the van. Right, I would like you to pause the video now and attempt to answer this question, and then once you've finished answering the question and you've got an answer, we will move on to the next slide to go through how you should have solved it. So Jess will remain in contact with the van's roof as long as reaction force R is greater than 0, is what I said on the last slide. And we've got this diagram over here to help us think about it. So you've got mg acting down, reaction force acting upwards. Okay, and obviously the centripetal force is going to equal mg minus r. So we need to consider that r is 0, because that's the maximum speed Pat could travel over the bridge. And when r is 0, we can put that into the equation that the centripetal force is equal to mg minus 0. And therefore, working those through, we get mv squared over r is equal to mg. We rearrange them to find what v squared is, and then solve to get the maximum speed that Pat could travel over the bridge will be 8.9 metres per second. Now, at the beginning of the PowerPoint, I mentioned that the most difficult questions to solve are circular motions on a bank track. Just looking at the time, I'm not going to have a chance to go through that in the PowerPoint today in time to get it on for you to have the lesson. So I'm going to discuss this in more detail with you in future lessons. But at the moment, we've got F equals ma towards the centre of the circle is what we would always consider. That's the case for all types of circular motion questions. What you need to do for bank tracks is consider components of the reaction force that are acting towards the centre of the circle. So in that case, we're going to have to use trigonometry in order to try and work out what component of the force is actually acting towards the centre of the circle. There's a link here if you want to follow that link. It should help you get onto to a website that talks you through this. I'll also post that link onto Teams for you so you can access it. But as I've mentioned before, I will go through circular motion questions on a bank track with you at a later date. I hope you've enjoyed having this PowerPoint for your lesson today. And yeah, let me know how you found the lesson overall. Thank you for listening, and goodbye.